Hello, my name is Ted Muelhaupt. I'm the Principal Director for Aerospace's Center for Orbital and Reentry Debris Studies. And today I'm going to talk about the particular challenges that these large constellations, these proliferated LEO constellations, have for space traffic management. So let me start by showing a profile of LEO space. I've been using a plot like this for some time now and been periodically updating it. And so what I've got here is I have thrown away all the latitude and longitude information and simply plotted the number of objects at any given altitude, and that's on the vertical axis. And so the count of objects is on the horizontal axis. And so if you look at that red line represents the current population in LEO, the number of objects that are at a given altitude. And yes, this is an average. So the population density, the tracking density, is what drives the number of conjunctions and collision avoidance alerts, and is essentially the environment that a given operator will experience. Now, over on the right, in blue, I've got some operators to show you where some of the different operators at different altitudes are. And so that represents the current population. Now, debris is also populated on here, and so the space fence is about to come on operation. And while the red line represents things at about 10 centimeters and above, the gray line represents things at about 5 centimeters or above. So we expect when the space fence is fully in operation, we will eventually settle in with a much, much larger catalog, and almost all of that's going to be debris. Now, that doesn't literally change the risk environment, but it will change the perceived risk environment because those operators are going to see a lot more conjunctions. Now, the actual risk is that blue line, and that's 1 centimeter above, and we generally think that's fatal. And so ideally, we'd like to avoid all the fatal objects. And so in an ideal world, we'd be doing collision avoidance on that blue line, not on the red line as is currently done. Now, new space is going to change the profile of this. And so what I've got superimposed on this are these green spikes. And the spikes represent the number of objects in a constellation at that altitude in just one generation. And there's 100,000 of them on this current plot in green. Now, if you look, those spikes are projecting well above the current perceived current catalog. So the number of collisions, or conjunctions rather, that you're going to see at any given altitude is going to change quite dramatically when these new constellations launch. Furthermore, there's a huge volatility in this. This plot doesn't look a whole lot like the first generation of this plot that I produced, because a number of constellations have changed where they're going to operate. They've withdrawn from the market. They've shelved their plans for now. Those are the ones in yellow. And so even from a planning perspective, these new constellations are going to change the environment, and they're going to change it in a way that probably won't match this plot. But if you're a current operator and one of these new constellations parks next to you, you're going to see a dramatically changed environment, and probably by orders of magnitude, by just about any measure I've ever heard applied to space traffic management levels of operational activity. So let me give a bit of a history lesson on how collision avoidance has historically, traditionally been done. We look about a week out in advance, and by we, I mean the Space Surveillance Network, currently the CSPOC, and it looks for conjunctions that might occur. And if the conjunctions cross a threshold, then action might be taken. Now, we don't look much more than a week because the probabilities and uncertainties have grown to, probabilities dropped and uncertainties have grown, so that it's really not worthwhile looking much more in advance than that. Now, if they see a worrisome conjunction and it's across a threshold, they will notify the operators. And if it's a live object, they will probably look for better data, increased tracking, and look at it again over the next couple of days. And so every day they look at the probabilities that are predicted for that conjunction. And if they stay high, then maybe we think about doing something, and the operator might plan a maneuver. If usually you want to do this no later than the day before, because the further in advance you do it, the smaller the required maneuver. But it's up to the operator as to whether they're going to maneuver or simply ride through the conjunction. And if they do it far enough in advance, they may be able to combine that action with something they're doing for some other purpose, such as drag makeup or station keeping. Now, most conjunctions are debris versus debris, and since neither can maneuver, generally we just watch. If it's a really tight conjunction, we might worry about the debris from that collision and look at that, but generally we're just watching. If it's most of the other conjunctions are going to be debris versus an active satellite, and then you're only dealing with one operator who has the active satellite, and since they're the only one, at least initially at risk, it's their decision. Sometimes, however, the conjunction is active versus active, and now there are a bunch of open questions. Who maneuvers? What situations? What are the rules? Is there a right-of-way? If there's a conflict, who adjudicates the conflict? And for that matter, who calls who? And who can put responsibility on the other if they choose to ignore and the other one doesn't want to? So all of those are issues for even traditional conjunction analysis and collision avoidance. And I will note that even if we do plan a maneuver, that maneuver is not necessarily checked to see whether it creates some new conjunction or some new problem. So it isn't even a given that an action to mitigate a risk actually mitigates the risk. Proliferated LEO constellations have their own special challenges because they will launch hundreds to maybe 1,000 satellites in a given shell. I've seen some operators plan for 1,500 at a given altitude. And so it isn't just a matter of one satellite, it's many at the same location. So if another vehicle is at an orbit near that shell, there will not just be frequent but repeated encounters with members of the shell. If you don't encounter vehicle 400, you might encounter vehicle 251. The closer an orbit matches the shell, the more opportunities there are for problematic conjunctions. We found that you need about 10 kilometers of mean altitude separation using traditional external data to keep the vehicles far enough apart that you don't see large numbers of conjunctions. Now, you may see, if you don't do that, you could see thousands of conjunctions a day. And within the constellation, with large thresholds and poor tracking data, you can see tens of thousands per day. Now, that may not be a problem for the owners of the constellation because they generally don't worry about self-conjunctions. They know where their vehicles are. But perhaps it is a problem for an external SSN agency. And of course, these vehicles don't just magically appear in their final orbits. You have to transit to and from. So launching satellites into these shells, they're crossing other orbits. If you're transiting yourself, you have to encounter the shell, and you've got lots of opportunities, and particularly for launch cola, large covariances mean lots of more problematic conjunctions. So transiting to and from can be a problem. And finally, there's only a finite number of places where you can even put these shells and keep them reasonably far apart. So let me show you an example. We made up a constellation and we put 1,200 satellites in a sun-synchronous orbit at 98 degrees and at 1,000 kilometers and very, very close to circular. And we park those near what we're calling the old constellation, which is 6 satellites at 63 degrees inclination, are also at about 1,000 kilometers, but they have a little bit of eccentricity, a little bit more tolerance in their orbits. And we looked over a 30-day period to see how many problem conjunctions there were. And if you have the kind of data that is purely from external tracking that is routinely published by spacetrack.org, then you ended up with a couple of hundred ones that cross at least one operator I know's threshold for paying attention. If you're down to, you can accept more risk, and if you accept a 1 in a million risk is where your threshold is, then that number drops down to 129 over the 30-day period. And if you say 1 in 100,000, it drops down to 50 of them. And so you can throttle the number of warnings by the level of risk you accept. Now, if you had better quality data, if you had the kind of quality that is typical with the high fidelity propagator, well, then those covariances shrink, the number of conjunctions shrinks, the probability changes, and now you're down to a much more manageable number of conjunctions. But if you had the quality of data that goes with GPS, if you had onboard GPS and got your position knowledge down to meters, well, now these two satellites are two systems, constellations, are happily interacting, and there were no COLA alerts for the 30-day period. So the quality of the data that is available and the threshold that you choose for a warning will greatly change the number of conjunction alerts you're going to get. But there's an added wrinkle that goes with these large constellations. Virtually every operator I've talked to is planning on using some form of electric thruster, low thrust system. And furthermore, they're going to put in a very high degree of automation, including automated collision avoidance and station keeping. And so what this means is that the vehicles can adjust their orbits, and may frequently adjust their orbits depending on how the algorithms are set. And it does so without human intervention. So the operators may not even know that a vehicle is maneuvered until after the fact. It may, next time it passes over a ground station, they get telemetry, they may see that it has done a small maneuver. So it isn't a matter of screening maneuvers and filing a flight plan with someone, because these operators may not even know their vehicle is intending to maneuver. And so what all this does is that it invalidates the assumptions that go with the traditional COLA process I described. I can't predict a conjunction a week in advance if I have no idea if one of the vehicles involved in the conjunction is going to maneuver or not. And I can't tell if I'm going to miss a conjunction because a couple of vehicles may have maneuvered and created a conjunction that's happens well inside my 1 week screening thing. So the normal process that we've used as a community for collision avoidance simply doesn't work, because it assumes the vehicles are where you can predict where the vehicles are going to be, and without knowledge of maneuvers, you can't predict that. Now, there's an inherent lag between somebody observing a maneuver and being able to get it into the catalog and get it into the screening. And even a tiny maneuver will, at the very least, add to the covariance because the orbit's not quite right. So the timelines of our current catalog process and the timelines that go with these autonomous station keeping and maneuvering things that a large constellation must do are fundamentally incompatible. Now, these large constellation owners, all the ones I've talked to, are relying on an external SSA service to warn them of incoming traffic. And if they can't share the maneuvers, if they can't tell the people where they're going to be because their vehicles are on auto drive and did a maneuver, well, then that process breaks down. So the whole process is dependent on being able to look far enough in advance to plan for a conjunction. Now, of course, if you're operating two satellites near one another, this whole problem is greatly magnified. So to sum up, these large constellations are going to provide some particularly special challenges for space traffic management. The huge numbers are going to change the operations environment by orders of magnitude, at least locally, and by virtually any measure that this new space activity is changing everything by orders of magnitude. And so maintaining separation between them is problematic because LEO space is finite and there aren't any particular rules about parking one on top of another. And the biggest problem is that these autonomous and low thrust maneuvers invalidate the very assumptions that go into current COLA practices. So what this means is that we're going to have to develop new practices and new approaches. First off, if you're going to operate these numbers, you've got to drive down the covariances, and that means sharing information probably owner-operator data from onboard GPS level accuracy and shared in real time. Autonomous maneuvers are pretty problematic, so we've got to deal with the automation, and further automation is probably the answer to some of that automation. And we may need to step away from just considering point-to-point conjunctions. The traditional assumptions don't work, and so maybe it's time to be looking for a whole new approach. Maybe we look at probability densities within the shell or within a tube within the shell. New approaches might give us some other way of dealing with this. But for all of this, we need a central place to share our information and to make this available to one another, because no one operator has it themselves, and numerous bilateral agreements probably are not workable. So the bottom line is that business as usual is not going to work. And to deal with it, we need cooperation, and that's literally co-operations.